So, hello, my dear student. I'm Shweta Sharma, ECL Mathematics faculty. Today, on account of National Mathematics Day, I have a very special guest for you. Here in this session, Mr. Jonathan Crabtree from Melbourne, Australia. He is with us. A very warm welcome to you, sir.
Thank you very much. Namaskar, namaste, namaskamaru, wherever people may be in India. I know your welcomes are very different, like all of your people. I'm very honored to be talking with you today.
So guys, Mr. Jonathan is a mathematician who is researching on Indian mathematics, which is called Bharatiya Maths from last 37 years. So I would like to request Mr. Jonathan, sir, that please tell us about how you got interest in Bharatiya Maths and how Bharatiya Maths is different from Western mathematics.
That's
Please,
a
sir.
Yes, certainly. Thank you for the question. I first became interested in the problem of why mathematics is confusing in 1968 when I was a little boy, aged 7, in class 2. What I noticed when I was in class 2 was that Bharat's zero, Bharat's shunya, was missing from my teacher's explanation of mathematics. So later on, I decided in 1983, after noticing many confusing things about mathematics, that we're told to follow rules without necessarily obeying the rules, understanding the rules. We just obey the rules. We memorize formulas without understanding. In 1983, I set out to fix mathematics. I know that's a pretty absurd goal for anyone to have because nobody ever thought that there was anything wrong with mathematics. And yet, through my schooling as a child and then as a young man, noticed things just seemed a little bit silly. And many rules didn't make any intuitive, common sense understanding to me. So in 1983, I started to explore mathematics, and I started off, as you can imagine, with Vedic mathematics. And I looked into that quite a bit, and I looked at all of the other speed mathematics books around. But they didn't really give me an intuitive understanding of what was going on in mathematics. The Vedic mathematics was great for giving me some interesting speed mathematics tricks, as they're often called, unfortunately, perhaps. But I really wanted to understand how it really worked. Like I wanted to pull mathematics apart as if I was an engineer and understand all of the bricks and the foundations and how it all fitted together. And I didn't ever have that. So I set out in 1983 to try and come up with an explanation of mathematics that would make sense to a child in class 2. So although I've become an old man in the meantime, my goal has always been to be able to explain maths to young children in a way that they will intuitively understand, as if, oh, well, that's simple, that's common sense, I understand that. And so the Bharatiya mathematics, I kind of came back to the mathematics of India. And along the way, after starting off with Vedic mathematics in 1983, I also explored mathematics in ancient Greek, Sanskrit, Arabic, French, German, Italian, Russian, Dutch, Czech, Spanish, around about 19 different languages. But about 6 years ago, I really started to focus on the mathematics of Aryabhata, Brahmagupta, and Bhaskara the first. And I kind of I mean, people had translated their shlokas many times, and people knew about, for example, the laws of sign of Brahmagupta. But nobody had really taken a very simple bird's eye view of mathematics to say, what's the big idea of Brahmagupta? What's the biggest idea of Aryabhata? What's the biggest idea of Bhaskara? And what I've done is I've simplified the ingredients of Indian mathematics. So now it's almost like I feel I could explain mathematics to my children in the same way that Brahmagupta would have explained mathematics to his children. And so there are many things that are confusing in mathematics that now I know can be very easily understood by children in class 2 and class 3 that probably confuses many of your students in class 8 and 9 and 10. They know the rules, but many students like myself, we weren't taught the logic behind the rules in a common sense way. So I'm answering the second part of your question about how is Bharatiya mathematics different. Well, the mathematics that's taught all around the world is based on a Western understanding of mathematics that came to us via the ancient Greeks. So in particular, you would have heard of names like Euclid and Pythagoras and Thales and so on. And in the Renaissance in Europe, they started to rediscover the mathematics of the ancient Greeks. And what happened is they took, for example, in particular, book 7 of Euclid's Elements as the kind of the Western Bible of arithmetic, because book 7 of Euclid's Elements was an explanation of arithmetic, number theory, as line segments. So it didn't have any numbers in it, this book of Euclid, but it was about the geometry of line segments, which we would measure today with a ruler. But what happened is the ancient Greeks didn't have any concept of zero. They didn't have the number 1 as a unit. So they had no 0 as a number, they had no 1 as a number, and they had no negative numbers either. And yet that's what Europe and then England took as the foundation of mathematics. And they developed all of their explanations of mathematics without 0, without the number 1, without the concepts of positives and negatives being balanced in symmetry. And that became the way that the British Empire began to spread its mathematics to all of its settlements and colonies around the world. And this is hundreds of years before the writings of Aryabhata and Bhaskara and Brahmagupta had been translated into the English language. And so the way that we were told mathematics works, the way that was established and settled in all of the schools and universities was before people really knew about the Indian astronomers who were the real generators of the mathematics back in the year 499 with Aryabhata and 628 with Brahmagupta and so on. Hundreds of years passed, but over those hundreds of years, it's kind of like become lost in history, the simplest ideas of Indian mathematics. And so I first met an Indian professor of mathematics in Hungary, strangely enough, and I was speaking at a conference on mathematics in Hungary, and this Indian Dr. S.R. Santanam said he didn't know about this Indian mathematics, and he invited me to tour India. So that was my first tour of India, and you met me on my third tour of India at ISA in Pune. So it's a very strange thing that just because I was a stubborn detective wanting to work out how mathematics work because I wasn't happy with it, I've just been like a detective. I've been trying to work out who murdered mathematics. And so I now have all of the history as if it's a detective story. And that's what I'm starting to share with people in India now about how it really was meant to be taught, but never came to be taught.
Right, absolutely. So guys, my dear students, as we discussed and Mr. Jonathan gave us so many knowledge about our Indian ancient mathematics, I just want to say that this is a journey of 500 before years. It's like we can say Shunya to Anant, zero to infinity. Now, as of now, you know today is the National Mathematics Day, Ramanujan birthday, and Ramanujan who knew infinity. So we can start this journey with zero. So I just want to ask Mr. Jonathan because he did, he gave his life 37, 38 years for Indian mathematics. I just want to ask him how Indian mathematics is very, very important, like Brahmagupta, Aryabhatta, knowledge, it should be in our all students should be aware of these Brahmagupta journey, Aryabhatta's and Bhaskara Rai's life journey, and now Jonathan is a part of this journey. I'm really grateful. I'm saying this with my heart that this is our Indian students are really very very happy and very very grateful that you meet us. आप हमसे मिले students. I hope you will be inspired for him. He's a great mathematician. And sir, can you tell me, could you please tell me how can we introduce Indian ancient mathematics concept in Indian curriculum at primary school?
Well, I'm hoping that Narendra Modi and all of the ministers in the Ministry of Education will watch this video that you're helping me with, Shweta. It's really a case that I'm talking about the ideas of these ancient rishis, but what I'm wanting to do is to convert them into cartoons for children and games and songs for children. So what I'm not going to be doing is focusing on a lot of dry text from the Sanskrit. What we need to do is to entertain children and make the ideas fun. So the fun and games really is all about putting aside the concept of number. It's not about the words, it's not about the symbols, it's about the play. So let me give you a quick example, and a little later on I'll show you some slides that will also go into this as well. But let me give you a quick example of a game about selling bricks. You know, houses are made from bricks, and imagine that the bricks are made of clay. So imagine a child is a builder, and the child has a spade and a bucket. That's all they've got. And the bucket has square sides to it. Now, the child can dig up the clay and put it into the bucket and fill up the bucket and then turn the bucket upside down, and the sun will dry the clay and make a brick. Okay, so that's how we might imagine a brick is made. We just dig a hole in the ground, fill up our bucket, and the sun will dry that cube-shaped brick of clay into a brick. So imagine a child in class 1 is going to play a game. They're going to sell bricks to another child. And the child who's the brick seller has 2 bricks for sale, okay? But what if the child comes along and says, I want to buy 5 bricks? Oh no. The child wants to buy 5 bricks, but the seller only has 2 bricks. So what will the child do? The child will dig a hole and fill up the bucket and make a brick. And the child will dig 3 holes to make 3 bricks. Okay? So the child then has the 2 bricks at the start plus the 3 bricks that she just made. So she's got 5 bricks now, and she sells them. Okay? And everyone's happy, but guess what the child now has? 3 holes. Okay? So that's a kind of a game that children can just look at bricks and holes and imagine digging with a bucket and a spade. And if we let a brick be like 1 positive and 1 hole being like 1 negative, then we start off with ground level 0, and 1 brick goes up 1 and the hole goes down 1. But if we put the brick in the hole, we get back to ground level 0. So we can have bricks be positives and holes be negatives, and we can get children an understanding of adding and subtracting bricks and making bricks and selling bricks and buying bricks. And before you know it, we can then say, well, let's count how many bricks we've got. And they haven't been writing numbers yet. They haven't been drawing symbols. They've just been playing a game and role-playing these little happy Harappan Valley brick seller games. But the children will then say, well, if I've got 1 brick and the purchaser wants 4 bricks, well, then I'm going to end up with 3 holes. And so 1 minus 4 equals -3. And the child will start to understand that in class 1. So at the moment we teach positive numbers in class 1, and then we wait until about class 6 to introduce the concepts of negative numbers. But then we do it in a very confusing, wrong way, because back then we'll say that negative numbers are less than 0. But I'll just leave you for now with the thought that all numbers represent counts or measures of quantity. And in the universe, there's only 2 things. There's energy and there's matter. And the least amount of matter you can have is 0. The least amount of energy you can have is 0. And if numbers represent counts or measures of quantity or energy, the least number representing a quantity you can have is shunya. And so negative numbers are not less than 0. That's the mistake that came in from Europe. So let me leave you with that thought, and in a little while I'll share some slides with you, and I look forward to perhaps maybe later on after the video some questions from the people who watch this. But it's an exciting journey to realize that many of the confusions that you've had are not the confusions, they're not your problem, they're not your weakness, they're not your stupidity or your lack of intelligence. If you were ever confused by mathematics, you were probably right to be confused, because the structural foundations from the West and the British Empire in particular are wrong. So thank you for watching.
This is really very, very interesting way of teaching maths. Fantastic, sir. Fantastic. Seriously, our student will love this lecture. Very nice. Sir, I just want to request you, if you want to show some slides to our students, we can start.
For this YouTube talk, please answer my green questions live via the chat on the top right-hand side of your computer screen. Do not chat or ask questions unless I ask. This talk is how Podometic Bharatiya Maths reconnects maths and science. And again, my name is Jonathan Crabtree from podometic.in. Elementary maths foundations concern counts, measures, and relationships between quantities that reveal predictable patterns, and counts of absolute value binary operations. The role of zero as a number, defined by Brahmagupta as the sum of equal yet opposing positive and negative quantities, was neither grasped in the Middle East nor transmitted to Europe. So we can see in India in the year 628 the transmission of zero as a placeholder, yet not as defined by Brahmagupta in the year 628, began. So the zero as a placeholder began in India and then went to the Middle East, to Iraq, to Baghdad, where Al-Khwarizmi investigated Indian mathematics and wrote a book about Hindu arithmetic. And that was in the 9th century, about 200 years after Brahmagupta. From the Middle East, it went to North Africa and then to Italy with Fibonacci, and then to Robert Record in England. But I can imagine that Robert Record might have said, Brahmagupta, I wasn't told about your zero definition or your 18 sutras of zero, positives, and negatives. So neither negatives nor zero appear to have been involved in the development of Arabic algebra. But first, some ballet. Notice the way she is spinning. Which way is she spinning? Answer in the chat box. Just type in your answer. Is the dancer spinning right and clockwise, or left and anti-clockwise? Type your answer in the chat box. Like mathematics, she spins both ways, right and clockwise, and left and anti-clockwise. And there you can see the same image clearly presented to your brain, spinning in two different directions. So our mind will perceive mathematics in a way that is unique to us. And yet we have seen the evolution of mathematics happen only towards 1/2 of our foundations. That's what happened in the West. So complete the phrase. Answer via the chat. For every action, there is an... What do you think it might be? Type it into the chat box. Equal and opposite reaction. And that is Newton's third law of motion. So actions have equal and opposite reactions. Let's look at one negative electron plus one positive positron. Together, they equal to 0. They annihilate each other and release a little bit of energy in the form of a photon. Now, symmetry, the heart of Indian mathematics, symmetry is when things are the same around an axis. Seeing symmetry and discerning when it breaks is a key for understanding both mathematics and physics. Imagine a big bang, which would have been silent. In space, nobody can hear you scream. But it's as if shunya was decompressed, creating infinite magnitudes and multitudes from 0. And from the Big Bang, we can consider the zero-sum universe, the conservation of matter and energy, and Newton's third law. And from the foundations of mathematics of Brahmagupta and Bhaskara and symmetry emerges my own mathematics, Podometic, which is an update or a replacement for arithmetic. So consider planet Negatron off to our left, or is it off to our right? And consider planet Positron. And in the middle, in that static view, if there's a body between them equidistant to both planets, there is 0 gravity upon that body. So wherever opposing quantities or forces or directions are equal, you will find 0. So here we have a simple number line with a smiley 0 mediating in the middle between two opposing multitudes and magnitudes. Now we need to consider in our framework of mathematics, in our meta-mathematics view, our bird's eye view of the foundations of mathematics, what I call the 0-point choice. Now here we have Escher's artwork, which I've put a couple of straight edges into the artwork. Now, when we draw a point, we need to make a decision from that point, using our straight edge, which way do we draw our line? We can draw our point in 2 opposing directions with our straight edge. We might have our point and then draw our pencil off to the right, or we might have our point and draw our pencil off to the left. And both of those directions can be equal and yet opposite, just as if you walked east and then you walked west. So from an arbitrary point, which direction do we go? Well, the west says we only ever go off to the right, and we call that direction positive. And yet Brahmagupta's ideas were not applied 1,000 years after the time of Brahmagupta in the 7th century. And yet those ideas should have been applied, because Brahmagupta's ideas were about symmetry. His ideas of mathematics were empirical, based on scientific observations of how the universe worked. Yet the ancient Greeks, they based their mathematics on philosophy, and from the philosophy emerged a geometry in which they didn't have 0 or 1 as numbers, and they didn't have negative numbers. So 1,000 years after Brahmagupta, we had René Descartes, and it's from Descartes that we have the Cartesian plane today, and yet the Brahmaguptan plane is superior. So Brahmagupta's 5 addition sutras are pretty much what you would expect them to be. No surprises there. And yet the zeros and negative terms are in 4 of Brahmagupta's addition sutras. And what we will find out if we explore the sutras a little more is the word negative, positive, and the word 0, they appear so often in the definitions, that the sutras, the laws of Brahmagupta from the year 628. We have subtraction, we have multiplication, we have division, as well as the addition sutras. And on the screen, we also have Brahmagupta's original Sanskrit. Now, we look at Addition Sutra 4, and that is the magical element of mathematics that got lost when Brahmagupta's 0 went to the Middle East on its way westward. Addition Sutra 4, when positive and negative are equal, the sum is 0. So here, let us imagine that we've got 1 black positive and we've got 1 red negative. So when the positive and the negative are equal, the sum is, as you can see, 0. If we've got 2 positives and 2 negatives of the same size or multitude, again, the sum is 0. So 0 can either be an absence of everything, or it can be the sum of everything. So we have taken away 2 positives, 0 minus 2 positives. What do we see? 2 negatives. From 0 again, this time we will take away 2 negatives. 2 red negatives go away. 0 minus 2 negatives leaves 2 positives. So when positive and negative, the sum, when positive and negative are equal, the sum is 0. So imagine this line is ground level 0. We can add integers to 0, and by integers, I mean the positive and negative whole numbers. We can add integers to 0, and here I've created the B line, a Brahmagupta version of our number line, which has implicit symmetry in it based on his Sanskrit shlokas, his sutras. And so off to the right, we can see we've got counts of positive units, positive black ones. And to the left of the 0, we have counts of red negative units. And it doesn't matter whether black is positive or black is negative. Whatever we choose, the other number will be the opposite, an opposite color, and together one of each or two of each or infinity of each will all sum back to Brahmagupta's 0. So just as we can add integers to 0, we can also subtract integers from 0. And as we saw before, whenever we subtract one integer, one color from 0, it results in the opposite color. Whenever we subtract positive from 0, it results in negative. Whenever we subtract negative from 0, it results in positive. So we can put together both the addition and subtraction of integers, and we get this symmetric pattern. Where off on the right-hand side, we have addition of positives and we have subtraction of positives. Subtraction of a positive will give you the negative, remember. So that's why there are opposite colors on the right-hand side of the midpoint 0. And on the left-hand side, we have addition of red negatives and we have subtraction of red negatives. Subtraction of red negatives will give you positives. So now we can apply the Indian logic to Descartes' multiplication. And this diagram is from 1637, and this is the first diagram that led to the development of the Cartesian plane. And this is in French. And as you might have guessed, René is a French name. So let me read the translation. And we've got the diagram with two lines, the axes. Across the bottom, we can consider it an x-axis, and going up to the left, we can consider that a y-axis. But let me translate the words of René Descartes. For example, let AB be taken as unity, or 1, and let it be required to multiply BD, the multiplicand, by BC, the multiplier. I have only to join the points A and C and draw DE parallel to AC, and BE is the product of this multiplication. So let me make this a little simpler with an electronic version. So here I have a GeoGebra app, and you can see the web address, so you can play with this yourself. So what we have, if we look at the legend, we have BD across the bottom in blue is the multiplicand, and we have BC going up to the left is a green line for the multiplier, and then we have BE is the product. Now, if I just extend out the multiplicand, we see that, which is the blue line, we see the red line, the product, increases. So I've extended the blue line, and as you can see, the red line has increased. If I reset it again, this time I'm going to extend the multiplier, the green line, and we will also see the product increase. So we have increased the green line And through the property of similar triangles, we can see that the product has increased as well. So let's reset again, and with this geometry, we now introduce the concept, the point choice I mentioned before. So we can say, let 0 appear at point B, and let a line drawn to the opposite side of B be negative. So now we can have a negative multiplicand and a negative multiplier, and we see together they both produce a positive product. So a negative multiplicand and a negative multiplier results in a positive product. Now this should have occurred to Euclid in 300 BCE. This should have occurred about 2,000 years later to René Descartes, but it didn't. So here we have another applet which is on the standard XY Cartesian plane, and I invite you to play with it so you can see the relationships between the similar triangles and the geometry of both positive and negative line segments. We also have another applet for division, because proportion works for both multiplication and division, and importantly, proportion is preserved across both negative and positive. And yet all of the proportion theory that developed in ancient Greece only dealt with what we would say today are positive magnitudes. So let's look at Al-Khwarizmi's 6 equation types. Arabic algebra entailed steps to arrive at co-equal polynomials. So the following is an anachronistic styling as modern equations. But Al-Khwarizmi didn't have equal signs or exponents written like this. So we have, for example, ax squared equals bx is an example. We have ax squared equals c as an example. And you might have heard about Al-Khwarizmi's technique was balancing equations. And if we just imagine a pan balance like this, you can imagine ax squared is balanced with bx, or ax squared is balanced with c. Or what about bx is balanced with c, and ax squared plus bx is balanced with c? Now, what you might have noticed is that what's missing is a polynomial in the form ax squared minus bx equals negative c. How could you have a positive term on the left of that balance pan equal to a negative term on the right-hand side? The Arabic world and Al-Khwarizmi never understood Bharat's algebra, which encompassed both zero and negatives. We also never had an equation come out of the Arabic world such as ax squared plus bx plus c is balanced against 0. You can imagine a set of balance scales would never make any sense in this form, and it didn't emerge in the Arabic world. And so let's consider Al-Khwarizmi. What did he say? Let me say, I had seen that the Indians had set up 9 symbols in their universal system of numbering. 9 symbols? And every number put together above 1. So Al-Khwarizmi did not mention 0. 1 is the root of all number and is outside number. It is the root of number because every number is found by it. But it, 1, is outside number because it is found by itself. I mean, without any other number. So Al-Khwarizmi did not mention 0 and did not consider 1 a number. So what if we move from Al-Khwarizmi to Al-Yuqlidisi about 150 years later? And he said in his book, why are the Hindi letters 9? So much for the 9 letters. 0, the aim is only to occupy the place. We multiply the letter to occupy the place. Tell that there is a place and that it is empty. Now, these are key phrases. There's much more in between them. But what we find is that Al-Yuqlidisi considered 0 an empty placeholder and not a number. And that's again because from India, we had the transmission of 0 as the placeholder, yet not as defined by Brahmagupta. India's 0 concept as a wonderful concept that embodies 0 and positive and negative. Well, the concept of the 0 and the negative seemed to have vanished to nothing on its trip to the West. So we must fix maths. And the way that we do this is to have independence from the British. Because the British Empire is their mathematics, it's Greco-Anglo. It's Greek and English mathematics, built without 0, without 1 as numbers, and built without a concept of symmetry with positive and negative mediated by a 0. And the British math that they spread throughout the colonies and settlements of the British Empire was only built for 1, 2, 3, and so on. So we must simply Brexit British maths myths and rediscover Bharatiya 0-built mathematics with the beautiful symmetry. Off to the left we have 0, 1 negative, 2 negative, 3 negative, off to negative infinity. And off to the right we have 0, we have 1 positive, 2 positive, 3 positive, off to positive infinity. So if we look at arithmetic, which is what developed in the West, we can see that the child's mind is obscured because the ideas of index laws and multiplication makes more, negative numbers, it's all about rules, not reason. The integer ordering is wrong. The number words make sense. The laws of sign are wrongly explained. And we find that children around the world do not like Western arithmetic. They fear it and they fail it. And sometimes they enjoy it. But wouldn't it be wonderful if, having rebuilt Bharat's beautiful mathematical foundations, that Narendra Modi brought about the revival of a mathematics I call Podometic, which is Bharatiya mathematics. So the child's mind, the maths mind of the child, is illuminated fully with common sense, multi-sensory games, fun, songs, toys. It's intuitive. There are stories. And children love Bharatiya mathematics. And so we must now accept that the mathematical foundations of ancient India are true and the mathematical foundations of the British Empire are false. So now you know. Arithmetic is based on ancient Greek ideas. It arose before India invented zero as a number. The ancient Greek math was 1,000 years out of date by the time Brahmagupta wrote his sutras. So the evolution of elementary maths is beginning again. Thank you. This has been Jonathan J. Crabtree, and now it's back to you, Shweta.
Thank you, Mr. Jonathan, sir. This is a great pleasure to meet with you in this online platform, and this is very helpful for our student also. Sir, I just want to ask you, if my student want to connect with you, how can they connect with you? So please give us little bit information regarding this.
Sure. I'll just let you know that, as you've probably seen in the presentation, the website is simply www.podo.in. That will take all of you to the website, which is all about Podometic Bharatiya Mathematics. And just as you've learnt about arithmetic, I call Bharatiya Maths Podometic. So it's, instead of arithmetic, it's Podometic. And that will all be explained in some children's books coming up. If people would like to contact me, there are a couple of ways that they can do that. They can hunt me down on Twitter. My Twitter username is simply @jcrabtree. So that's twitter.com/jcrabtree. Or if you'd like to send me an email, you can simply send an email to info @podo.in. And I look forward to hearing from you. And in particular, if you found anything that surprised you, let me know. If you found anything that was totally a shock or a surprise, let me know. If there's also anything that you want to be explained in more detail, let me know. I'm always interested to hear what people think, and on my website, podo.in, you'll see I've got feedback from people like you, not just from India, but in over 70 different countries. I have a YouTube channel. Simply search for Podometic, or it's youtube.com/Podometic. So I'm also on Facebook. You'll find me there. I'm on Instagram too. So there are plenty of ways to get in touch with me and to find more about what I'm researching. And I'll love to hear from you. Thank you very much. I feel honoured to be speaking to you on the anniversary of the birthday of Ramanujan. He and I share, I think, some behavioural aspects. I'm completely crazy for understanding mathematics in a way that people think I'm a bit bonkers, a bit crazy. I sleep on the floor. I wake up every night, and several times each night, dreaming about mathematics. I love dreaming about mathematics because that's often when the ideas come to me. So I kind of feel a little bit like Ramanujan, that the ideas are coming to me, and I feel very privileged to have these ideas gifted to me, and I'm wanting my ideas in turn to be gifted back to India, because it's really your heritage, your Hindu mathematics, your rishis and gurus, that really their knowledge has been lost. And as you now know from my talk, the reasons why these ideas vanished, but they're too important. India has too many problems that need solving, whether it's air pollution, a drought, how to get a good income from your job. all of these things are going to be greatly helped if you have the right insight into the language of science, the language of engineering and physics, which is mathematics. And it's India's own mathematics, it's Bharatiya mathematics, which is consistent with the laws of physics and the laws of the universe. And so if we're going to be unlocking secrets for another 500 years to come that put Indians on Mars, it'll be perhaps with the help of Aryabhata, Brahmagupta, Bhaskara, and all the others that have had such an impact that unfortunately went missing in the West. So, namaste again. I wish you a very happy and healthy National Mathematics Day. Stay healthy and safe, and I hope to see you again when I'm next in India. Thank you so much for the invitation to talk with you. Thank you, Shweta, and also to Israel. You've given me a wonderful privilege on National Mathematics Day. I wish you all the very best of success in your futures.
This is our honor, sir. You came to address our student on National Mathematics Day. Happy National Mathematics Day to all of my students. Thank you, sir. Thank you so much.
Thank you. See you soon.
Thank you.